am Shanawaz. In this lecture we will characterize p-primary abelian groups with some given conditions. So to start this lecture we will first define so we know that if G is a p-primary abelian group, then G mod PG, where PG is prime, P is prime, then this is a vector space over a finite field, say FP. So we denote this dimension of this vector space. So the dimension of this vector space over this field FP is denoted by D of G. So let us make this a definition here. So we have a definition. So let G be a finite p-primary abelian group. Then we denote dg d of g. This is the definition. So we denote this to be the dimension of the vector space G mod PG with over the field FP, a finite field of P elements. So then we had this characterization of p primary abelian groups with dg is equal to 1. So this is the characterization. So it states that if G is a finite p primary abelian group, then dg is equal to 1 if and only if G mod PG is a non-zero scalar group, is a non-zero scalar group. So this lemma is the characterization of finite p primary abelian groups with dg equal to 1. So now to prove this theorem we need some results. So this is the first result which we are going to need to prove this lemma. So this is the proposition. So this proposition states that an abelian group G is simple if and only if G is finite group of prime order. So an abelian group G is simple if and only if G is a finite group of prime order. So let us prove this. First we prove one direction. So first we'll assume that G is a group of prime order. So let G be a group of prime order. then G is cyclic, then obviously G is cyclic, because we know that any group of prime order is cyclic. So then G is cyclic and hence abelian. Now order of G being prime implies that G is simple. Also order of G being prime implies that G is simple. So we are done in one way. Now by a simple group we mean a group which has no non-trivial normal subgroups. Now let us prove this direction. Now let us assume that conversely let G be a simple and abelian group. Let G be a simple and abelian group. We had to prove that this group G is of order a prime number. Now G being simple and abelian means that any subgroup of G is normal, and so then now G being abelian means any subgroup of G is normal, then any subgroup of G is normal. But G being simple means the only normal subgroup of G are the identity subgroup and the G itself, and so the only normal subgroups of G are so it is this group E and G itself, where this E is the identity element. This is the identity of G. Now let us consider a non-identity element in G. So let us consider an element X in G which is not the identity element. Such that now so the subgroup generated by X is obviously G, because G has only two normal subgroups, has only two subgroups, identity element and G itself. So if X is not identity, so X will not generate this subgroup here, so X has to generate G. So so if we consider X to be a non identity element in G, then this is true. So we claim that X is of finite order. We claim that X is of finite order. Suppose not. So if this is not true, then all distinct powers of x are distinct elements. Then all distinct powers of x are distinct elements. So this is true because suppose two powers of x are same. Suppose xm and xn, they are same. So this implies x to the power m minus n, that is the identity element. So that means x is of finite order. Now g being generated by x implies g is of finite order, but at the beginning we have assumed that g is of infinite order. So that is the reason. So no two distinct powers of x can be equal, because if these two powers are equal, then this implies that x is of finite order. So if all distinct powers of x are distinct elements, then x and x square, they are not equal, and hence this subgroup which is contained in x, this is a trivial subgroup. So this is a trivial subgroup. So this means G has a non-trivial subgroup, a subgroup other than this subgroup here, the trivial subgroup, which is not the case because G is simple. So this is, which is a contradiction. So hence every x in G, every element x in G is of finite order. Now let order of x be m. So if m is prime, then we are done, because if m is prime, then G is cyclic and hence abelian. So there is nothing to prove in this case. So we will assume that this m is composite. Let us write here, if m is prime, we are done. Therefore assume that m is a composite number. So m is KL, while KL are positive integers other than 1, where K and L are positive integers other than 1, because if one of them is 1, then m is prime. So now let us consider the subgroup. Now clearly, if we consider the subgroup, this the subgroup generated by the element x power k, this is a proper non-trivial subgroup of x. it's a proper non-trivial subgroup of X. Subgroup of I mean this X, i.e. G, which is again a contradiction. So this is again a contradiction. So this forces M to be a prime number. So hence order of X is P, a prime. So this is a prime number. So hence we are done. Therefore G is a group of prime order. Now there is one more result which we are going to use in the main lemma, I mean this lemma over here, and this lemma is states that so every group of order p square is abelian. So we know a group of order G, suppose G is a group whose order is p to the power n, then ZG, I mean the center of G, is always a non-trivial subgroup of G. So in that case ZG is always a non-trivial subgroup of G. So since this order of G is p square, ZG so if G is equal to ZG, then G is abelian. There is nothing to prove. So let us do this way. Let's do it this way. So let Z of G be a proper subgroup of G, because if this is equal to G, then G has to be abelian. So there is nothing to prove in that case. So let us assume that ZG is a proper subgroup of G. But by Lagrange's theorem, every subgroup of a finite group divides the order of a group, but order of ZG divides the order of G, i.e. order of ZG is either equal to 1 or p, because it cannot be equal to p square. So this is same, this is equal to p square here. So order of ZG divided p square. So this is so order of ZG divides order of G, which is equal to p square. But order of ZG cannot be equal to p square. In that case ZG is equal to G, but we have assumed that ZG is proper subgroup of G. So there are only two possibilities for this number. So this number is either 1 or p, but order of ZG cannot be equal to 1. The reason being, a group of order p to the power n has a non-trivial center, because a group of order p square, sorry, let us make it more general. A group of order p to the power n has a non-trivial center. Here G is a group of order p square. This n is equal to, this n is in n. So here G is a group of order p square. So order of G, so center of G will be non-trivial. So this implies order of G is equal to p. Now let us consider the quotient G mod Zg. Now order of G mod Zg, which is same as order of G divided by order of Zg, which is same as p square over p, and that is equal to p. So the quotient group G mod Zg is of prime order, hence cyclic. Hence G mod Zg is a group of order of prime order. Therefore G mod Zg is cyclic. Now where is our result? If this quotient is cyclic, then G is abelian. Hence G is abelian. So we are done.